Hello, everyone. Welcome. Thank you so much for joining us this morning, or this morning if you're in the UK. I just wanted to very quickly welcome you all and say thanks for coming. As you know, we have built our first Skylark project in the UK just in the last few weeks. And we wanted to take the chance today to tell you a little bit about what we learned through the process. So this is what this morning is about. And I will be handing over to the team in a second. I just wanted to let you know the session's being recorded. So if you have to go, it'll be available in a little bit after we finish. And any questions that you have, please just pop them in the comments. We will get to questions and answers towards the end. And without further ado, I am going to introduce Jason.
Thanks, Mel. Hi everyone. Welcome. So just to give you a brief background on the project, so Pig's Barn is a self-built project managed by our client Tim. So when the WikiHouse team came on board, the double garage with an upper floor office was already approved by planning. So we provided the chassis model that fits the planning constraints. And along the way, we also provided some architectural advice and specifications. And yeah, working with Momentum, our structural engineer, which did an amazing job in making sure the barn stands grounded and doesn't fly away. We managed to produce 91 different types of blocks in time for cutting. So this is Chop Shop, our CNC manufacturer, also did a brilliant job in cutting and assembling 7 packages of around 248 sheets in a matter of 2 weeks' time before delivery. So the WikiHouse team volunteered to help assemble the chassis on site. And so this is where our journey began. So as you could see, Tim, our client, managed to pre-install the foundation and the sole plates. And the pallets that you're seeing, they are basically for storing the blocks, but we relocated them to the area next to the site so we could carry the blocks over. And Momentum and the WikiHouse team drew up a plan of where the anchor bolts would be positioned. And also we also specified the sequence of work for installing the foundation and the anchor bolts. And the image on the right, as some of you might have seen it, Mel has shared it in the community chat. This is the foundation detail that we're currently reviewing them to make it a standard detail so we can share it with you guys in the library. And yes, so Chop Shop managed to squeeze in all the blocks in one mega lorry. And with the help of Tim's neighbor and also the forklift and the lorry's driver, we managed to store the blocks and group them according to the types and also the assembly steps in 3 hours. And one of the problems that we encountered during installing the wall blocks was that some of the sole plates were slightly too wide for the slots to fit in. But that's no problem. We had to improvise, and we use a multi-purpose tool to trim the slot holes, and that fit perfectly. And by the end of day 1, we managed to slot in almost half of the wall blocks. As you can see here. So here's a quick time lapse of what we did on day 1. As you could see, one person could easily lift one wall block, and we also created this sort of assembly line where we laid out all the blocks, and one of us would be cutting the slot holes, and one of them would be carrying them over and slotted them in. So the following day, a perfect sunny day, so Tim and his neighbor decided to help as well with the build. And also we had Chop Shop and the photographer who helped during the rest of the half of the day. So what we realized was that this side of the saw plate was didn't fully align with the wall blocks on the other side. And fortunately, Tim had a circular saw, so and he managed to trim the saw plate along its length, and we could easily slot in the remaining of the wall blocks because of that. So lesson learned: always allow enough tolerance for the foundation rails. If yeah, you're also using concrete slab or different types of foundations. So while the rest of the team was doing the sorry, I think there's oh, sorry. There you go. So while the rest of the team was installing the wall blocks, some of us started to install the combs on top. So because some of the insulation was were filled all the way to the top and they could easily get caught, so one of us had to basically push down the insulation down and also mallet the combs in. And we did all of that for the rest of the elevations. And in the end, we malleted the bow ties in, which fit perfectly. The next stage was installing the floor blocks, the upper floor blocks. And yeah, they were quite heavy. So we already prepared the genie lift in the middle of the chassis. And one of the problems is that the genie lift didn't lift all the way to as expected, 4 meters high. And also the surface wasn't flat enough. So we improvised by putting pallets on top of it. And the idea was to hook one end of the floor block into the combs. And while they were installing the floor blocks, the other side, the other team members installed the staircase. So some of us could actually go up and basically direct where the floor blocks would go. So the sequence of work was that we installed the floor blocks from outwards in, and this image on the bottom right, it's the last block, and we put like a timber placeholder on top of it, and all of us went up and basically just easily hammered the remaining floor block in. So yeah, so here's the timelapse of what we did for the floor blocks. And this is how it looks like. So once the floor blocks were properly installed, we installed the end. We wanted to install the end blocks. So because the end blocks came without insulation, so we had to cut the insulation and put them, slot them into the end blocks. So what we did was we created 2 layers of the insulation, and the middle part is to allow the combs to go through. But we also found where some of the insulation got caught, so we had to put our hands in and basically to make sure that the spaces were filled to prevent cold corners and cold bridging. And so once, while the other team was doing the insulation, some of us were pegging through the wall blocks, and we found it quite difficult as well because because the insulation just gets caught when we peg through. So we had one of us to actually go on top and push down the insulation to make way for the pegs to go through. So this was already towards the end of the day, like around 8 p.m., and it was about to rain. So we had to quickly tie back the chassis and call it a day. That's our journey for day 2. And yes, we're now letting the bow ties in as well. So after a tiring day on day 2, well, I became jelly by then already. So it was yeah. So yesterday, the day before, we had 10 people, and day 3 we had around 5 people, and we were all quite tired. And basically, the aim was to our goal was to finish the gable walls, the verge blocks, and also the roof blocks. And we encountered some difficulties installing the combs into the gable walls, because like the previous day's problem, the combs just get caught with the insulation in the gable walls. So we had to remove some of them and refill them again. And when we were installing the verge blocks as well, there was some design misfits, so we had to cut them. So we spent a lot of time installing the combs and the verge and blocks, and it wasn't what we expected. But Alistair went back the following day to help out to finish up the remaining of the roofs. And so I'll pass it to Alistair to talk to you more about the rest of the journey. Over to you, Alistair.
Thanks, Jason. I'll leave you in control of the slides. So yeah, you can see this is it was really a half day. This is the day before that Jason was talking about, but you can, it's a really interesting observation here that you'd think the main bulk of the work would be the thing that takes the time, but actually what ended up absorbing most of our time were those combs and verges. And you can see then the next day where Tim drafted in some builders who'd been working with, was a very brief video there, who were brilliant. There, and they were kind of, it's always really funny when you introduce kind of professional builders to WikiHouse for the first time, because to start with, they're like, what on earth is this? But then within a few hours, they were like, you know, they were just on it. Not even that really. So yeah, the actual roof part then went really, really quickly once, you know, through those blocks. But then lo and behold, when we got to the other gable wall and all the verges and combs, again, we slowed right down again and kind of got stuck. So maybe next slide, Jason. Don't know what we've got there. Yeah, you can just see some of the kind of progress. There was also, we've been a bit worried about, there was this one special kind of, which is not, we don't think is really the best way to do roof lights actually. This is one special roof light block in there, which was absolutely huge. It was way too heavy. It actually wasn't, even with its weight, it was actually kind of fine. I mean, probably helped by the fact that the builders were kind of, you know, burly guys. And in general, we want to make WikiHouse not reliant on having burly guys around. It should be something that anybody can build. But it was actually fine getting them up there, especially with this one, because it was quite a low floor. It just wasn't too much of an issue. It was the combs and the pegs and the end verges that were caused us tricky things. We had this, yeah, made this nice space. Cool. So let's go to the next slide. Oh yeah, and so then we sort of eventually then after that, the way they got to was like where they got the roof on, and this was a really interesting point as well, that because of all the struggles at the top, they really had a struggle getting the last bit of roof in. So with the downstairs, everything had just fitted in perfectly. The last block was like, you know, very, very smooth and tight. But because of all the knock-on effects of things being not quite straight around the end verges, that then meant it was a real battle to do that. And they were using the multi-tool, what I call the butter cutter, to kind of hack bits to try and make sure that could work. And they got it there, but it's a really interesting point. One of our interesting takeaways, obviously, this being the first Skylark build, we wanted to see how the overall accuracy did. And it was amazing, right? So along the length of the building, The deviation from the computer model, I think, was about 3 or 4 millimeters max. So incredibly accurate in terms of the overall dimensional accuracy, but that wasn't true of the ends and verges because of the issues we'd had. So it ended up being even a centimeter or so out the top left. Next image, please. You can see they're kind of wrapping it here. And I think I've got one more image, which Tim has sent me since, because in the days following, they then clad it, and it's going to have solar panels on and these roof slates on the roof. What I quite like about this is that it's quite sort of timeless traditional materials on the outside. So there'll be no, you know, in the Peak District, which is this kind of very picturesque area, as you'll see in a minute. There's no kind of outer signs that there's anything especially innovative about this building, which I quite like. It'll look, you know, just like slate roofs and everything like that. And this, obviously, the wood on the outside will silver slowly over time. Eventually, they got some scaffolding to do this, which was probably helpful. And so here is sort of finished with a unnecessarily cool drone shot, because Jason brought his drone along so we could get these cool shots of in progress. But you can see how just incredibly beautiful, how lucky we were really to have this as a sort of first pilot site, and why we'd been so keen to go up and join in the self-build, because it was just like a really lovely place to be for a weekend to build this thing, really. It's gorgeous sort of landscape all around, and yeah, you can see there how it kind of nestles into that part of the site. So, in summary, once we've finished our Hollywood shots, yeah, we saw this was our kind of main objective, was to go for this, really, was to go there and sort of we'd done prototype builds for kind of the launch event and during the structural testing and things like this, but actually you learn so much by actually building the thing on site in anger. And we got a lot of takeaways, really. So one was bow ties work brilliantly. They were one of the most pleasing things. They do a lot of work. So that thing is something a little bit magical. I should totally have put the meme into these slides, actually. You know, the Homer Simpson disappearing into the hedge meme. It feels a bit like that when you fit a bow tie. You kind of put the bow tie on and you hammer it, and it just goes, and it just disappears into the plywood. It's that junction works really, really well to tie the whole structure together. So we were really pleased with we've sweated the tolerances on bow ties, and they just work beautifully. The other thing that also really worked is we'd sort of thought it through, but we didn't know exactly how it was going to work. We wanted to get to this standard assembly sequence for lifting floors up and into place using a genie lift. And overall, we were pretty pleased with that. This sequence where you take it inside, you lift one end up onto the wall, and then use the genie lift to lift up the other end, and then you just move it across. So I think there's definitely, as Jason mentioned, there's definitely lessons about, you definitely want to have a genie lift that can do 4 meters or more. I mean, and this was a lower ceiling than most because of the garage, because it was a garage, and the planning constraints. But yeah, you definitely want a tall genie lift, and you definitely want a flat platform on top of it. But overall, it seemed quite promising that it was a pretty quick and workable way to lift up these lift up the floor blocks onto the tops of the walls. So that was nice. As I said, once you got going, the actual adding blocks bit, that just went really, really crazy quickly. So you can actually build the main bulk of it. So there's a real kind of 80-20 rule, in the sense that 80% of our time was spent on not even 20% of the parts, actually probably more like 5 to 10%, which is those verges and ends and combs, was what consumed 80% of our time. Whereas the actual building of 80% of the, most of the chassis went really, really quickly. We used this super soft insulation, so we've experimented with loads of insulation, and we're definitely really keen in future to keep exploring other types of natural insulation and stuff as well. But this super soft that we were using is made from recycled bottles, and it's really lovely. So it's not itchy. So self-builders all builders, but obviously self-builders especially hate using mineral wool because it's really, really itchy. It gets all over you, and you can't even, you shower, it stays on you for days sometimes. So this stuff was really nice. It's just like a big fleece jacket. It's not crazy cheap, but it's recycled and really, really lovely to work with. So we were big fans of that, except for the issues we had around pegs and combs to talk about. chassis was really accurate, as I mentioned, that it went really quickly, despite the fact that most of the time, most of our team were not skilled laborers. I mean, we've had experience with WikiHouse, but we wouldn't class ourselves as skilled, as having any kind of carpentry or construction skills, really. And the other general thing is that the great thing about spruce, so obviously there is definitely, of interest, especially with everything that's going on at the moment, the possibilities of using other materials like OSB, and maybe we will experiment with that. And I can definitely see large pro operations might get into looking at, but spruce is so nice because it's really, really lightweight. It's lovely to work with, and yeah, if you do get an issue, you can get the multi-tool out and just quickly hack it. So that was all the good things. Then there's what did we learn? So these are our main lessons, really, sort of summarized, and we've touched on these as well. The other one is allow tolerance for foundation. So obviously what you've got with WikiHouse is you've got a chassis that's really, really accurate, but the real world is not accurate. So the foundations have to do this job, and the foundation connections have to do this job bridging between an inaccurate world and this highly precise chassis. Now, we had allowed for tolerances, but what I think it was at least plus or minus 5 mil either way on those sole plates, those foundation rails, as I call them. But in the end, they hadn't been able to get the exact size. The actual size was actually larger than we expected, and that had used up the tolerance, the room for maneuver, if you like. So basically our takeaway rule is you can probably leave too much, but always make sure that we've got the sizes of timber that you're expecting to get, and that you're leaving tolerance, so that if the foundation rails are not quite in exactly this, they're not quite straight, or they're not quite in exactly the same position you're expecting them to be, it's not a problem. There's enough give that you can reposition the chassis onto them, and that will be true even with other foundation types. Obviously, this was not unusual. This was one of the foundation types is putting it down onto a slab because it's going to be used as a workshop and garage underneath. But the same would apply even if you were putting it onto a suspended floor onto rails as well. Always have paper assembly manuals on site. Now, again, this wasn't really a new lesson. This is definitely something we've learned before, but in the speed, we were thought, oh, right, well, we'll just get it on site, because Tim had wanted to move really fast with the project, and so had we. We wanted to just try it, get it on site, and everyone did an incredible job to get it done and on site in a matter of weeks. But we hadn't made paper assembly manuals. And the problem with that is that it means it concentrates power and knowledge in the head of one person who knows the structure. And so people are constantly pestering that person and asking them questions, but also they feel disempowered. So assembly manual, paper manuals, like these sort of IKEA manuals, are really, really important, because they kind of flatten knowledge on site. So everybody can see what they're making and what things go where, and they don't need to be kind of centralized around a single person. So we've been like, oh, right, well, it's going to take long. And actually, we just said, no, this is not working. Went home, threw some very basic ones together in an hour, and that was fine. So even basic paper assembly manuals are better than having no assembly manuals. The other one, which we'll touch a bit on in a minute, is making sure, particularly for self-builders who are not necessarily experienced project managers, making it really clear what the tasks and responsibilities are and who is responsible for what. And I think that this is a really, really crucial thing. And so Jason, we're going to show a piece of work that Jason's doing to kind of help with that in future, and we're going to test that and share it. So more on that in a minute. Generally, I threw this one in as well. Again, this wasn't news to us, but I think it's worth mentioning. Oftentimes when people are approaching us, and there may be others, you all may encounter similar situations if you're using WikiHouse, is that sometimes people will turn up with a design that they've already done in great detail. And in the case of Tim's, he already had planning permission, so he had very, very little leeway as to changing the design and the dimensions of the design. This makes work so much harder. So it's much, much easier if you can decide you're going to use WikiHouse, go with the standard sizes, and then that very quickly you can generate basically the design you want. But because in this case the design was very, very like, okay, you know, that height of that window must be this many millimeters, not that many millimeters. It meant that huge numbers of the parts had to be made bespoke, and this created a lot of extra design work for Jason and for Letitia at Momentum Engineering to kind of bespokeify it. So basically, if at all possible, don't absolutely finalize the exact dimensions of the design before deciding to use WikiHouse, because you can do it, you're just going to create a lot of extra work. It's much nicer to go, I'm going to use WikiHouse and then roughly use the basic standardized modules to get that design, and then you won't be left doing that. You can just use the standard modules basically instead of having to make bespoke ones. And then the final one, which has been pretty obvious through everything that we've said so far, is that this recognition that most of our issues, most of the stuff we were encountering was related to pegs and combs. And that was particularly three things. So we already knew that combs were really hard work from a design point of view. And in fact, you know, if you go on the library now, it's quite coherent to see all the other blocks, and then you get to combs and it's like, it's so complex that Jennifer even had to make a whole tutorial video about how to get your head around combs. So we already knew that combs were a hassle from a design point of view. But then when we got on site, we found that, you know, it's really hard work putting the pegs through. I mean, then we had this issue where the insulation was getting in the way, so you have to clear it out. But then if you clear it out the way and put the peg in, you can then have this gap left behind which hasn't got insulation in it, and that's a danger. Because it's more work, you've got to get your hand in there and get the insulation back round. But if you don't get your hand in there and re-insulate it, there's a danger that you're going to have a cold corner, which is going to cause condensation and energy loss. So we were like, combs, what can we do about them? And we'll talk about that more in a minute. So I think that is that. I mean, maybe some of the others can join in now. We'll go to the next, and we'll talk through some of the things that we then did to respond to these lessons. So Jason, do you want to talk about this one?
Yes. Yes. Yes, as Alistair has mentioned, it would be good to have an idea of all the typical tasks that that's involved in a project. So we've created this Gantt chart on Notion. So this is based on a 2-story, 2-bed house, and the idea is to organize all the typical tasks in one view, and breaking them down into different packages, like 20 packages of milestones of tasks. So instead of following the usual work stages, so the idea is that anyone, self-builders, if you can choose which task that you want to do it yourself, or which task you want to outsource for professional help. And so the next step would be to test it on different projects, and eventually we want to publish it and share it with the community with you guys and get your feedback on this. So yeah, still work in progress, but yeah. So so in terms of improving combs and packs, I'm gonna hand it over to Clayton and Gabriella to talk to you more about how it works.
Thanks, Jason. I'll lean on Gabriella a bit when you can talk about the sort of structural implications of this. But just from an assembly perspective, there's obvious frustration there. I think in principle, pegs do work themselves as a sort of dowel in terms of attaching the structure together. But insulation caused some issues, and we have looked at other insulation methods. Blown cellulose is a possibility, and we're potentially testing that a little bit on some for an upcoming project. But given the way that CNC machining works, you end up with lots of little pocket corners at all the joints. So it just means that it creates a lot of dust, and potentially some of the cellulose might leak out of those. So it also means you have to have blown cellulose equipment on site, the reverse hoover to fit it all as well. So which adds a bit of complexity. So if we can solve the insulation at the manufacturer's end, we're keen to do that. And also at the same time eliminate combs, which is probably the main sticking point rather than pegs. So Jason, if you move on to the next slide. So that was the previous detail, which you're probably quite familiar with. So if we get rid of combs, there's a few ways we can do it. The main purpose of the combs is actually to keep the structure sort of vertically tied together. It does a little bit laterally, but most of that work is done by the horizontal bow ties around the walls. So we want to try and find a way that we can use a different connection method between floors and walls, and then walls again, to tie the whole structure down, sort of in terms of uplift and gravity loads. So the thing this is one of our first options we've been exploring, which is to use bow ties, which we know work quite well, but use them vertically as well as horizontally. So in this case, there wouldn't be any combs at all, and we'd have enough bow ties that would give that sort of capacity to tie the structure down to the rest of the structure below, and then into the foundations. And these could be installed afterwards, but like we do the bow ties on the walls, just get malleted into place. We could add a couple of screws into those little ears at the top to keep the bow ties in place. There's a little like H biscuit in the side there you can see, and that's for helping guide, because we don't have the combs there anymore, helping sort of guide and position the floors on top of the walls in a sort of neat way. It's a little bit of a lock between each of the pieces as well, because until the bow ties are in the side, fixed into the side walls, we don't have anything constraining it, the structure sort of laterally anymore. If you go to the next option, option B here is where instead of having combs, we look at sort of having a backing plate that is actually part of the wall structure. And so it functions in a similar way to combs, except it doesn't sit sort of centrally in the space anymore, which means it makes insulation much easier. And then still using full pegs, we just use little sort of mini dowels, what we're calling biscuits, which could then just be tapped into place. And they sort of act like exactly the same way the pegs do, but there's no process of installing combs, which means that it's much less material. And also I think the sequence is a bit simpler. And yeah, these are sort of pronged ends then to the walls that sit inside the floor structure, and you put these little pegs through. So that can be done both the inside and the outside.
If I just say one interesting thing about this as well, Tim, while we were on site, had a really good idea about pegs, which was to make them slightly, because sometimes you're using the peg to sort of squeeze the building down. And so you had this idea of having a peg that starts off, basically has an extra unnecessary redundant bit at the end that's narrower, so it's easier to get in, and then you mallet, so it then trains the building down. So it might be that we could do a similar trick with these biscuits as well, to have that little bit of redundant thing, but it makes it easier to kind of get it in and force the building into shape. Yeah.
And if you go to the next slide, Gabriel, maybe you can talk a bit about this, but we're trying to test some of these connections because we don't really have any data for how they behave in terms of sort of the vertical strength. So yeah, Gabriel, do you want to explain what we do next?
Yeah, absolutely. So based on the concept that we came up with, the idea is to test the load path. So we know that the force is going to travel through the what we call the biscuit, and then through the plates that we designed. So we now are going to have an experimental program in collaboration with the University of Strathclyde. We have a brilliant student, Aidan, and supervised by Marcus at University of Strathclyde, which are keen to work on WikiHouse with us. So we're going to get in the lab in the next weeks. And apologies for the horrible sketching. You can see the Clayton's model is much better, but these are our specimens that we're gonna test in tension, because as Clayton was saying, that connection in engineering terms is called hold down, and that's exactly what it does. It prevents the wall to uplift. So we're going to test them in tension and provide that experimental data in our guideline. Actually, the experimental program is a little bit more ambitious. So among these two connections, we're going to test them both, and then we're going to see which one performs best. And then we're going to embed this connection in a full-scale testing, which we're going to do probably in October, November, or a little bit more down the line. So yeah, we're going to keep you updated on that, on how it goes, and publish the information in the engineering guideline as soon as we have
it's worth mentioning, isn't it, Gabriella, that this speaks to those of you who watched the launch or at the launch. This speaks to, you'll probably remember us talking about one of the big main sort of structural challenges we still want to overcome with Skylark is lateral stability. So it's ideally, we'd love it if you could make 3-story structures. But the main challenge is that the way that the building will flex in the wind. And when we did those big tests before at BRE, the main constraint on that, and Gabriella, you tell me if I've got this right, is basically the pulling up, is that as the wind hits that part of the building, it pulls up the foundations. So this pull-up effect isn't just about, it's not just about the pegs thing, or can we get rid of pegs and combs, but actually not only can we find another way of doing the hold down job that is easier to build on site and causes less hassles and issues on site, but actually can we do it better than combs and pegs were doing it anyway, so that we can improve the overall lateral stability of WikiHouse Skylark and even get us to a point where maybe we can begin to think about 3-story structures.
Hello. Yes, we have a comment from Tim, if you can see that below, around insulating with a pump. Do we have any thoughts around that?
Yeah, so this was something that we talked to. So Tim's here. It's cool. Tim,
Hi, Tim.
This is the Tim. Yeah, and this was something that we talked about. I don't know if you've done this, Tim. We should probably have this on the call. Had him on the call actually. Basically, the idea is to say, if you've got like a expanding foam, whatever product, this was the great, which is that you can have where you have this danger of the cold corners being left behind. What Sim's suggesting here is yeah, exactly, that you could put in an extra expanding foam and go and fill out that corner. But I think, which is a good, it's a hack, but I think it is a legit hack. But yeah, we thought, let's see if we can go one step further altogether and just completely get rid of them, because that would just mean that we have a complete insulated block, and it would hopefully solve both problems. Yeah.
Amazing. So yeah, we've given you a lot of information. And as I said, if you have questions, just pop them in the comments. I know that Gabriella has prepared something on vibrations, some testing that you did after we left the site. So if you want to talk about that for the next few minutes, I'll hand over to you.
Thanks, Mel. Well, first of all, we probably want to say thanks to Tim too. Oh, I think there's a question on pegs.
There's some more questions flying in. So yeah, let's do those.
Yeah.
Can you see that? There's a question from Jennifer.
Yeah, instead of replacing pegs.
Yeah. Wouldn't it be possible to think about a tool that would help place them?
Yeah, I think you'd still have Clayton, I don't know what you think. I mean, I think you'd still have the issue with the insulation. And the other thing was also combs themselves caused issues. A, they were difficult to design, but B, also they, when you put the verge or the end piece on, it has to be exactly straight. And if it's not exactly straight, it doesn't, so you end up with millimeters in accuracy. So we just think there's probably a lot of reasons why, if we can just get rid of them entirely, it's going to be so much better.
And we have another question from James. How did we manage to have the entire structure delivered in one go? Was it easy to organize? Would it need more build area?
Well, unfortunately, Chop Shop dealt with the loading logistics, as well as the excellent driver that they had, who was very patient. yeah, they managed to pack it. It took a while. I mean, I think mostly to do with getting blocks out of their workshop and onto the lorry, and because they didn't have a lot of loading space. At the site wasn't so much an issue. We had to maneuver a little bit, which sort of slowed things down a bit, because we had a telehandler rather than just a forklift, so it did quite a big turning circle. But in terms of space for build area, it was about equivalent space of the build area that we needed for storing all the parts, wasn't it? So about the same footprint of the building next to it to unload everything into. That definitely makes a difference, having that bit of space there. I think without that space, you probably have to do it into smaller deliveries. So you sort of almost just in time, maybe do it a floor at a time, which is one route, but it definitely made more sense in this circumstance to put all together in one lorry load.
The one, so Tim was saying here about it was the cost, and it saved a lot of money having the farm. It was brilliant. It was like a farmer with a front loader forklift unloaded it, and that was great. The ideal would be, weirdly, sometimes if it's going a long way, putting it on a lorry like this in one go is kind of makes sense. This was coming from Sheffield, which is not, it's always about an hour's drive. Is that right? It wasn't that far, and in a way there's an argument to say it'd be nice if you had like just a Luton van. The problem is, unfortunately, the floor beams now of Skylark are just too big for a Luton van, which is a bit of a shame, really, because otherwise you could do it in like a few runs in a Luton van instead, which would probably have been easier.
We have a question about the process that we use to test new designs, and that one's for you, Gabriele. You want to answer that?
Yeah, that's a very good question. So there are standards. Normally the way you approach these things is that you know what sort of job every structural element does. So, for example, the column is working in compression, the beam is working in bending, and so on and so forth. And then you tend to design a test around the same mechanism, the same job that the structural element will do in a real life. So you tend to replicate that in the lab with actuators and stuff. And there are some standards that tells you, for example, the speed of the actuator, the number of cycles that you need to do. So everything is pretty much codified. And if happy to provide you more information if you're curious to any specific test of this. But there are specific guidelines that you can find telling you all the details. And so this is pretty much general level. If you have any further, I'm happy to follow up by email.
And Gabriele, you can, if you may have already seen these, Lachlan, but if you go to the engineering guide on the WikiHouse website, Gabriele has documented all the test setups and everything.
We have a question from Jennifer about those working on designs or plans already. Should they hold until?
Yeah, this is a really good question. I mean, if I'm being perfectly honest, there's always things when you learn a thing, you just want to act on it. If I were being perfectly honest, I'm not sure I would want to go back on site with pegs and combs again. It was fine. It was workable. It's just a lot more work. So if you're being lazy, it would be nicer to not. So we're sort of thinking about this, our timeline, and we're thinking it's probably going to be, what did we think, Gabriele? It's probably going to be a month, right, or so before we know what the outcome of those tests is, and then there'll be a bit of time for us to sort of re-release a new set of end blocks and stuff. But Clayton and Gabriele, do you want to comment on that?
I can probably comment that we are going to do some testing. That there's a way to calculate the expected performance. So probably if we feel confident that we have the design ready at architectural level, I would think that the performance can be calculated. I like that we normally in the team are very, very cautious, and we want to do things properly all the time. So we don't just design, we normally test and provide evidence with that. So we go a little bit a mile further. But everything that we have, I think, can be calculated even at this stage. So probably it depends probably on the structural engineer if he's confident or she is confident with the calculations.
I mean, certainly, by the way, though, if you're doing like a garden studio or something, you're probably, I mean, pegs and combs probably won't be much of an issue. You could, you know, I wouldn't worry too much. You can go ahead with the pegs and combs if you're doing a garden studio project in the next month or so.
Cool. We also have a question about wood types.
Oh yeah, well, this Clayton
yes.
Clayton can comment on this one as well. We definitely have used pine in the past. It's I mean, a lot, as much as anything else, it's been about sourcing it, because obviously make sure we're getting it from an FSC certified source, and what you can get in different parts of the world, as you say, ecoply in NZ. So pine seems to be fine. So those kind of softwood plywood seem to be the thing. Obviously, in the UK, we don't make plywood, apparently, because it's too windy. We only make OSB, and OSB is a bit harder to cut and it's heavier. So that makes a significant difference. That OSB is something more like 600 kilogram per cubic meter, whereas spruce is something more like 400, I think. So it's a significant difference. But generally speaking, because of everything that's happening with the geopolitics of plywood and wood and timber at the moment, we're definitely interested in exploring other kind of materials. Clayton, I don't know if you want to comment on that.
Yeah, and pine's not very common here as a structural product. It's sometimes used for boarding and things like that, but not really so much for structural sheathing. Spruce seems to be the main one that's available, so we've gone with that, and it's got good performance. But I know that other people in NZ and Australia have used pine before because it's readily available. I think it's also 19mm in New Zealand, which might make up for the slight difference in performance to spruce, I think. But worth checking. Yeah, we're looking at seeing what other options there are and other materials to test in the coming weeks, really. But for now, we try to keep at least a consistent level of baseline for the tests, so testing across a consistent material, and then we can also add to those tests with other materials once we sort of can ascertain whether they're up to the job.
One question from Zlatan: how does MEP work with the Skylark system?
On several different levels. I mean, there's lots of different types of MEP. So in terms of electrics, that should be fairly straightforward. There's a service zone built into the walls and into the roof. So if you're then putting a layer of plasterboard or something as an internal finish, you've already got a service cavity for running electrical wiring through. And where you need to go through, that should work between floors as well. There's a cavity down at the end of each of the floor beams. And anywhere else, you might just need to drill some holes. The depth of that cavity should be enough to take a Patras box for a wall socket with plasterboard on the inside. So that should make it easy. You don't need to put battens on internally. And that should work fine for most plumbing as well. So 10, 15 mil plumbing pipe should be fine. The big challenge is with ventilation and how you deal with ducting. We have put holes in the floor beams to run circular ducting through. It's big enough for 120 mil circular ducting. But you're sort of limited where you can put those and how many penetrations you can have. So it has to be sort of planned out really carefully. And that also has to work with the internal layout, of course. So one of the other things we've seen that the team in the Netherlands has done quite well is use rectangular ducting, flexible rectangular ducting, which they've run in the ceiling cavity. So the standard on the Skylark 250 series, the standard cavity in the ceilings is just over 70 mils, which should be enough to run rectangular ducting through. And that means although you'll have to make sure you can carefully notch where that rectangular ducting goes across the beams, you can fit it in that ceiling cavity, which should make installation quite easy.
It's still to be explored a lot, really, isn't it? I mean, this is going to be, we're going to have some fun exploring this. We think we've carved out more space than ever before, literally, for it. But more to learn, particularly around vapor barrier, the way it interacts with vapor barriers.
Yeah, and we had some challenges with how we deal with the solar vent pipe in this particular project as well, because obviously that takes up a bit of room, and it's much easier if that just goes directly down into where it drains out, rather than having to run a fall within the floor structure or anything like that. So.
Yeah, and so there was another argument for paper instruction manuals, because Jason had made a pre-cut thing for the soil pipe on a roof piece and a floor piece, but then we put the floor piece in before we realized we'd put the wrong one in the wrong place, so we'd have to recut it. It's not the end of the world in the sense you have to recut it, but it is another argument for always have paper assembly manuals on site. Oh, Mel, you're on mute.
If there's any more questions, we can keep you can keep adding them to the comment section, and we'll answer them. I'm going to hand over to Gabriella now to talk about vibrations.
Thanks, Mel. Yeah, actually, this was one part of the presentation we thought, in case we had a few spare minutes, just to give you an update of what we're being up to from the research side. So first of all, thanks a lot to team, which gave us this opportunity. So what we did on the building was we were interested in measuring the vibration sensitivity of the Skylark floor. For those who work in research, that quite a it's quite a hot topic and quite a question mark, in the sense of when we start using light materials like timber or even steel, because the mass of the system is not that much, not that heavy, the floor can become sensitive to footfall vibration. So it was a great opportunity for us to test actually the Skylark system. And this is a picture of the building. On the right side, you see the plan of the floor. So you see the stairs at the bottom, and those red dots are 5 accelerometers that we placed on the floor. This is a project that we did with the University of Edinburgh with Tom Reynolds. So we were both on site and tried to measure the performance on the floor. If you can probably, yeah. So you can see here details about the accelerometers. They are really, really teeny tiny. They're probably 1.5 centimeters a cube, 1.5 centimeters. They're really, really sensitive, and they are triaxial, which means that they measure vibration in the 3 directions. And they are connected to a logging box, which you see probably on the first picture on the left, on the right corner. And that box had probably, I think, had 5 times 3, 15, 16 channels. So 5 accelerometers measuring in 3 directions. And then we had another channel for a special hammer that I will show you in the next picture, which is pretty cool. It's a hammer with a sort of measurement system at the top. So when you hammer the structure very lightly, you can actually measure the amount of force that you put into the structure. So what we are trying to what's the research question here? So think about when you go into a swing and you want to go higher, what you're trying to do is that you're trying to push yourself at a specific frequency. So if you push yourself at a random times, you might not get higher. And if you think about that in engineering terms, you know, the structural engineers look at the world like a matrix. You think of that as a mechanical system which has its own stiffness. And what you're trying to do is basically you're trying to match the natural frequency of the system to bring the system into resonance. So every mechanical system has its own resonant frequency, which depends on the stiffness and mass of the system. And if you're able to excite the system at that natural frequencies, you bring the system into resonance, which means that if you are on a swing, you go higher. If you are on a floor or on a bridge, the vibration becomes higher and higher. And if you are far from that resonant frequency, well, nothing happens. So in the swing, you try to match that, but when you work with floors or you work with bridges, the problem is the opposite. You know that the people normally walk with frequencies between 0.5 and 2 hertz. So you tend to design floor systems which natural frequency has to be far from the walking distance, from the walking frequency of people. So if you change the slide, please, Mel. Exactly. So what we did, basically here, you see one of the tests that we did this is actually a working process, and I'm kind of halfway through the data. We perform some walking test, we perform some impact test. This is one of them. And you see on top, that's the hammer that we were using. So with the hammer, we were knocking the structure in specific points. And there's a loading protocol we're using. You see a typical input on the right, where we're actually giving 3 knocks, sort of light knocks, and then wait a bit and give other 3 medium knocks. And that allows us basically to record the response of the floor by the accelerometer, and then we can start understanding the natural frequencies of the system. So if you can please change slide. Basically, this is a plot which is actually one of the outcome that we got out of the monitoring campaign. On the left side, you see that blue rectangle. Those are the frequencies where people normally used to walk. So you tend to walk between 0.5 and 2 hertz. And you might have some harmonics up to 10 hertz, but they don't normally carry much energy. And the natural frequencies of the floor are in the range of 19 up to 40 hertz. So where you see the peaks, these 4, 5 red lines, they identify the natural frequencies of the floor. So the good thing is that basically the floor is quite stiff, so it can be brought to resonance by human walking, which is good, and that should have basically a very low probability of having adverse comments by user. That's a phrase that you normally find in the guidelines. Means is if you're sitting at a computer and someone is walking on the other side of the room, you shouldn't bounce, which is good. And then the other thing we did, if you can please change the slide, which was the other question we had, is do the beams work together or do the beams work individually when people are walking on top of that? And that's quite interesting, because from a design perspective, you only design beams to work individually, but then when you actually monitor, you see that the beams are working together. This look like heat maps, but what they are sort of vibration maps. So what you basically means is that when you look at the way the floor tends to vibrate, which we call mold shapes in engineering terms, the beams help each other. So instead of having the beam moving individually, the floors behaves more like a shell, and the 4 beams are helping each other, and that again contributes to have a little bit of extra stiffness on the floor. And then probably the last slide, which is as not super interesting unless you are into this stuff from a research perspective, is that you can estimate the damping on the system. And once you have natural frequencies, mode shapes, and damping, you can there's a standard that you can follow, and you can sort of assess the dynamic sensitivity of the floor. That you can actually put a number and say, okay, how many times during the day you expect the velocity of the floor going above a certain threshold, and then tells you again how likely you can be annoyed by other people walking close to you. So that's pretty much a little bit more on engineering terms, but this is some work we're going to do in the next few days and try to actually put a number and quantify, as this floor be likely to have problems with vibrations, or is going to be fine. And we suspect so far everything is pretty much within the range. So we just want to quantify that and have a number for that, which will be provided soon in the engineering guidelines. And I think that's pretty much all.
Yeah, I think the final, thanks, Gabriella, the final flourish to add on that as well, something that you observed and also Tim observed, is that there's the difference in the overall behavior of the floor, which looks fantastic, but then also a bit of localized bending just on the actual top panel of the actual floor beam. So probably one of the things you'll see in the next update as well is some additional noggin pieces. We didn't think they need to be very often, maybe like every 1.2 meters or something, just to make sure that just the individual panel itself isn't flexing. yeah, Tim's saying you kind of need some logins on there, so they'll be getting added in the next version as well.
That's brilliant. Thank you, guys. So we're about to run out of time. I just have one final question from Jennifer, which is: will we release the stair block soon, or will it be delayed due to testing taking priority now? Clayton, I think you might be.
It runs in parallel to testing, so we can we'll get them into the library and release them as well. They will be different to the ones that are used in this design here because of there's sort of quite a non-standard stairway width. The normal ones will be a bit more, I think, pretty much to exactly 900 wide. And we also look at whether we can borrow the winder idea that we used here and release that one as well.
Amazing. Thanks. So we've run out of time. So thank you so much for joining us. Thanks for the
Can we just also, by the way, as Gabriella mentioned it before, but just obviously a big thank you to the whole team, and also a big, since he's here, a big thank you to Tim as well, because I won't call him a guinea pig, but a pioneer. It's so fantastic to be able to go out and do a project, and it's a beautiful project, obviously in an amazing place, but also to give us the chance to kind of pick up all these things and then kind of immediately roll them over into the next project. So yeah, thanks to the team, and also thank you to Tim.
Amazing. Well, we'll see you soon. If you have any more questions, add them to the comments under the video. This will be the recording will be live in a few minutes, I reckon. So thank you very much. Goodbye.